For a little while now, I've been hearing conversations about foundational models, and if you've been following the machine learning community, you may have too. And I haven't fully grasped what they are, most importantly, why they're important. So, for his second time on the podcast, today I'm talking to Bruno Sanchez and Nuno, who, at the time I had him on, the first time 3 years ago, was the program director at Microsoft for their Planetary Computer, as well as for their AI for Earth efforts. Since then, Bruno has then started a nonprofit, the Clay Foundation, and runs as his executive director, and they have just released their V1 of what they are calling a foundational model for Earth.
It is mind-blowing that semantically indexing Earth, with all its implications for sustainability, climate change, biodiversity, all that stuff, it's doable. It's technically doable, and we have the data to do this. That, to me, is the most inspiring application you can do.
We go into the details of what this means, how it works, what the implications are, and how it might be useful. Of all the developments in machine learning applied to satellite images of the past few years, I think these foundational models and what Clay is doing, one implementation of it, is one of the things that I'm most excited about. Now, they're doing this as a non-profit, all in the open, and if big AI model that has a lot of implications started by a non-profit sounds a little bit too much like OpenAI in the early days, I also thought so. So I asked Bruno about this, and we mentioned ChatGPT more than once in this conversation, as well as their pivot to a not so much non-profit, not so much all in the open company anymore.
I will propose Litmus test if something is open or not.
All right, here's my conversation with Bruno Sanchez and Nuno. This episode is sponsored by OpenCage. If you're building any application or tool that uses location data, at some point you'll probably need to convert place names or addresses into coordinates, or coordinates back into place names. And this is where OpenCage comes in. They offer a worldwide, affordable, forward and reverse geocoding service that's easy to use. OpenCage builds on top of open data sources, which grants much more lenient licensing terms than alternatives like Google, allowing you to store the data as you want and even keep it after you stop being a customer. You can also display it on any map, all at a more affordable price. OpenCage handles all the complexity of dealing with the messiness of the real world and provides a simple-to-use API that allows you to focus on your use case. They have a generous free trial that you can use to get started with no credit card required, and they offer a clear upfront pricing with a cancel at any time, no questions asked policy. To learn more, head over to opencagedata.com. I'll have a link in the show notes. As a side note, OpenCage is also responsible for hosting the GeoMob events, as well as the GeoMob podcast, for which I'll also have links in the show notes. Thank you to OpenCage for once again being a sponsor and for their continuous support of the podcast. Usually I ask people how they would describe themselves, but you've already done that last time I had you on. So instead, I want to dive right into what you're working on at the moment, which is Clay, and we're going to get into that. But what I want to ask is a bit of a spin-off of that original question, but I'd like you to describe to me, as if I knew close to nothing about it, what a foundational model is.
We start deep into it.
Oh, we're getting right into it.
Of course. A foundational model is one really nifty trick of this type of AI, which basically front loads a lot of the computation for a lot of tasks. So normally when you need to do something with a computer or analysis, you do the whole thing from start to end to do the output. But foundational models, what allow you to do is to pre-compute a lot of the common things one might need to do for a lot of tasks. Like, for example, regardless if you need to detect faces or you need to detect pictures of cats or any kind of image, there is a lot of computation of understanding what is a circle, what is a corner, what is red, what is blue. Those kind of things will need to be done anyways. And that is what foundational model does. They were created for text ULM field. What's the best? The first approach that I know of, which was, imagine you have to categorize reviews of movies, like a little text of every movie, and you don't really have much text to work with. So a foundational model in that case would be to train a model with the entirety of Wikipedia, which is a lot of text, has nothing to do with movies, but you compute a lot of, and we can talk about how that works. Once you do that, you have a universal language model, and then you can use all that computation to be really good at understanding the text on the movies. So that's what a foundational model does. It pre-computes or front loads a lot of the computation, which makes a lot of sense for especially for Earth observation.
And so this is in contrast to building a dedicated model for every application that you have. So if we were on the movie reviews, I actually don't know how it works for text. So let's move to the images. That's a field I'm more familiar with. So let's say you want to do some segmentation task, for example, and you would start with a training data set. You would get some images, you would label them, you would build a convolutional neural network by training it. Here's the images, here's the output. You just take that small image and the label and you train that. And if you want to do a completely different task, you have to start over from a new data set and build that. Exactly. So my question then is, how is that different, if at all, from this notion of pre-training? So you have had data sets like ImageNet, for example, which is this very big data set. I think it's 100 million images of apples and cars and dogs and all of these things that already are labeled. You would train a convolutional neural network. This is, the height of machine learning 5-10 years ago, and then you would freeze some of those layers and you would train it on something like completely different tasks.
If you are if an expert on deep learning listens to this, they might disagree, but I think it's essentially the same concept.
Okay.
I think the difference is the things you can do with a foundational model. I think it opens you of many options. One of the options is, as you said, that you freeze the entire model or the layers, and then you replace the last one. So in the case of the Wikipedia example, you, instead of leaving the last layer, which is to predict the next word, then you put the classifier of the movies. Or if it's pre-trained on Earth observation, then instead of using the foundational task that we can talk about what that is, you replace that with whatever you are doing, which is detecting agriculture or doing those things. So you can do that, or you could create embeddings. And I love to spend time talking about what embeddings are, because the practice or the practical translation of a lot of these technologies comes down to embeddings. So you can use those things directly to, as if they were the original data, because by design they have most of the information. Or you can put layers on top, or you can do all kinds of things. It gives you a ton of flexibility, these foundational models, especially when you have very few labeled data.
You talked about a couple things. You talked about a foundational task. What is that, and what does that mean?
When you create a foundational model, you have an architecture, which whatever that is, internally, the layers, the neuron, all that stuff. Which, by the way, I think is worth mentioning that most of the revolution in AI, I would argue, which is, self-driving cars, detecting cancer in X-rays, translating, transcribing, summarizing, removing noise from all of it, in most cases, is exactly the same architecture. It's called transformers. And it's all this paper that called Attention is All You Need. And I think it's a fantastic human invention to create such a universal learner of things, which I would argue was not used for Earth observation at scale until the stuff we're doing now. That's why we created it, because we saw, hey, this stuff has been working in so many areas. Why not in Earth observation? Okay, so that transformer, when you do the foundational model, you're trying to do something that is universal so that it can be applied to any task, and you're trying to do something that doesn't need labels. So we do unsupervised. That's the unsupervised kind of learning mechanism. There are a few options. The one we use is called masked autoencoder, which basically you take an image, you remove most of it, and then you ask the AI model to reconstruct it. So in order to reconstruct it, it's going to need to understand the patterns. So if I hide one eye on my image, then after seeing a lot of images with and without the eye, then the model would assume, hey, I don't know what this is because I don't have access to any other information, but most times when there is a face, there are two eyes. So I reconstruct the eyes. So you're not using any label, but you're forcing the model to understand patterns that might mean semantics. That's a kind of foundational learning mechanism that you use to train a model for universal tasks.
This gets us into the embeddings. Can you then explain what the embeddings are and how useful they are?
So we talked about this an architecture with the transformer, and we can talk about what that is. But whatever it is just how the code and the layers are connected. Doesn't really matter. And then you have a task, which is the masked autoencoder, which is to remove part of the image and then repeat it. But then you need a way for that architecture, a thing to learn semantics, learn only the important thing, pay attention only to the important thing. And the way in most cases works is that this architecture are actually like a U. There are like two sides. One is the encoder and the other one is the decoder. The job of the encoder is to transform the input image into a very tiny amount of information. And then the job of the decoder is to transform that tiny amount of information back into the image. And then you compare both images. And if you did a good job, then there's no difference. And if there is some difference, the difference itself gives you an information how to change the parameters on this unit. It's called backpropagation. And for those who know about it, is the gradient, so the inclination of the error. How to update the model so that that little bit of information has the most signal and less noise. So in other ways, imagine that there is two teams, one team, and there are experts on everything. One team is the encoder, and the other team is the decoder. So one gets the image, but it can only pass to the other team a single piece of paper. They can write whatever they want, but they can only pass a single piece of paper. That is embedding. You can write anything you want, and it will write in mathematics, not in English. And then the job of the other team is to take only that information and then reconstruct that back the image. So you can imagine that in human terms, that the embedding of this picture would be there is a person which is speaking and has glasses, and it's just a little bit of information so that the other team can reconstruct it. In essence, what it means is that once trained, the embeddings are like 0.01% of the size, but ideally 99% of the signal, which means then everything you do is much faster, much easier to do because you don't need to handle all that complexity of the input image, just embedding.
You know, the first thing that comes to mind here is also, this sounds like an incredibly good compression algorithm. But when we think of compression, we don't think of, encoding the earth or really retrieving anything. It's really of, I am a data company and I need to send a lot of data because my bandwidth is limited. I'm a company like a YouTube or a Spotify, and I need to compress images, send that to people, and decompress it. But it seems like we've gotten to the same. The terms I'm hearing from you are very similar in a way. It's like we take this, we compress it down, and then we bring it out. But what I'm hearing, the main difference being here is just the scale at which you're able to do that. A good compression algorithm, it might bring it down 10x, something like that. And here we're talking like orders of magnitude better than that.
Well, you also have many more millions of parameters.
Exactly, yeah.
In some ways, yes, it is a compression algorithm because it all goes down to the embedding. But I'm only talking about the main use cases. There are use cases that also use all the intermediary layers. So now I'm just putting a filter and then just clear about embeddings. There are some applications where you still need the layers in between to do other fancy things. But in general, I actually love to explain that the project that I'm working on. It aims to be a lossless compression of Earth.
How do you get where are we today, rather, let's say? So lossless means that that little piece of paper, to use that analogy, you can reconstruct the exact same
Yeah,
image on the other side. You've
yeah.
lost nothing. And how do you have an idea of like how close we are to that today? Like, is it a really big challenge? Do we even need to be lossless?
No. When I say lossless, probably means lossy or
Okay, but like just a
semantically
little bit.
lossless.
Okay.
Yeah, because there are some things you don't want or you don't care. I don't know, like errors or maybe clouds for some cases you don't want to recreate it necessarily, or maybe perfectly the exact shape of a car or a building. Just there's a house, and then you can start adding details. I guess the answer to your question is that some applications list a certain degree of resolution, semantic resolution. Some applications need higher and higher and higher. The higher you go, the more difficult it is. If all you care about is forest, no forest, or deforestation, no deforestation, making a lossless compression in that sense to replicate, for example, tools like Global Forest Watch, we are there. We are already there. I genuinely believe we are already there to do that. And it was not done, and that's why we started this. But it I guess it depends on the application. But the Pareto, like the 80% of applications, I think we are not technically or data constrained.
What are the applications down the line? Like, why would we want something like that beyond it's faster to work with? What does that enable that wasn't possible before?
I think, as you point out, and internally we use these two classes of things we can do. One class is the faster, better, cheaper, which in itself is fantastic. It's probably the easiest way to sell this to a for-profit or for critical infrastructure, not only the quality, but also if you can do the same things faster or test it, that's fantastic. That's great. And there's everything you do in Earth observation, I would argue, you can do faster, better, and cheaper with embeddings. But there is also a new class of things. And
Sorry, on that first one, can you give me a few examples of what you mean? Like, we're talking again about these segmentation models. You were
yeah,
talking about
yeah.
Global
Okay.
Forest Watch, so that's mapping deforestation. Just a few seconds so that
Real examples with the model we just made. When you take Earth images, like from Sentinel, from these satellites from Sentinel, but it could be from others, one thing people do is to calculate biomass, how much carbon there is in the forest that you see. You calculate biomass with some physical equations. We can recreate more than 90% of the results using the universal embeddings, the foundational model embeddings. We train with a little bit of data for like 20 minutes, and we get more than 90% the same answers, much faster than the physical models. So calculating biomass is a huge application that has real implications for carbon markets and for quality and for others. Another one that is also real is land cover class. When you have an image, you want to know, is this urban, is this forest, is this agriculture, is this land, how does it change? Same thing using the exact same embeddings from the other case, because they are the universal ones, and we get more than 90% of the land cover on the land classification. With exactly the same embeddings, we can also make more than 90% accuracy of detecting aquaculture locations with a couple of human in the loop. So basically, we tell a human, hey, click in this map where you see aquaculture. And then we take the embeddings of those locations and we find similar ones. And then it finds more and it has some errors. The human corrects those errors, and in a couple of loops, we get 90% of the same accuracy. So these are three cases where we do three completely different things only with embeddings, and we get more than 90% accuracy with 0.001% of the input size with the same quality, which to me is just amazing.
So if I understand correctly, you are able to, because you create this model that's seen like everywhere on Earth, basically, and we'll get, again to the inputs in a little bit. It creates all these relationships between everything that it's able to see. So now you can take a new application, instead of spending a lot of time, a lot of people creating an entire new training data set, you just take a few examples. This model already has relationships between, many different things, nearly everything. So it's able to find what you're pointing out because it's already created those relationships. It doesn't know what they are. That's the self-learning aspect. But then you're saying, okay, this relationship that you've created between everything, it turns out that it's biomass or it's a land cover. And so just the main benefit here is that you just need a few iterations and much, much less training data. And it works across many different applications. You just need to basically find what those relationships are.
Exactly. It is a little bit of information that is specifically and explicitly designed to convey the most amount of the input image. And because it's designed to be a little bit of information with the most amount of the reconstruction potential, then you can use that little bit of information to do all the same tasks you would have used the bigger data.
So that's our first application. You said there was a second one.
That's the first class of applications. The second class is the super new things you couldn't do before. And part of it is being explored now because this is unknown. This is we are trained on the limitations of the former method. So I think it will take some time to figure out what those new applications are, because we have to untrain those limitations. But the one that gets me the most excited is that if we are able then to, these embeddings, these things are numbers, it's just vectors of numbers. And we are really good at making databases of numbers, slice them and do all kinds of stuff, clustering them, all the stuff. But now, those numbers are semantics, are things, are roads, river that is dirty or clean, or all those little things are numbers, which then means you can create a semantic index of Earth. So just like you can ask for data from Madrid and it goes fast because it's a number, let's locate from Madrid, or 2022, it's a number, let's go there. You could not do the same thing of deforestation in Spain or solar panels in Spain, because it would take computer vision, it will take a lot of effort to create that output and then show you. But once we have the embeddings, all we have to do is to go into that space of the embeddings, those clusters and those clouds of points, and then see what blob of those points are solar panels, and we tag them as solar panels, or are rivers, and we tag them as rivers. And then those rivers, we're probably going to have two little blobs. One is going to be dirty rivers or roads, paved roads and paved roads. And there are ways to do that, which we have already explored to do this automatically. But once you do this, then you can search. You can talk to Earth, to the dataset, and say, hey, show me places that were forest that are not forest anymore. Or alert me whenever there is, I don't know, an empty parking lot close to, I don't know, whatever thing it is. It's just mind blowing that semantically indexing Earth, with all its implications for sustainability, climate change, biodiversity, all that stuff, it's doable. It's technically doable, and we have the data to do this. That, to me, is the most inspiring application you can do.
So this is one of the big promises of a lot of Earth observation, is that it's not just seeing one thing at one time, but it's monitoring change over time. And so we've had, I think historically, these big projects like Landsat, Sentinel, that take a lot of data, and we've handmade many different models to look at many different things. So if you're looking for garbage, you're going to have a team that's dedicated on working on just that. If you're working on deforestation, you're going to be working on that. And what you're saying, if I understand correctly, is we can just keep taking all of that and find everything, basically find all the differences over time, and try to, then we can come in and say, oh, this change that you've seen, that's deforestation, and we can start tagging it like that. And so in the end, you have this index of all the changes and what hasn't changed, and you can query that.
And that is, to me, the amazing part is that all that is already in the data. It's locked in, lost in the pixels. Many of the answers of a lot of our problems are scattered behind pixels that are hard to index. Now we have a way to do that.
And so this gets into, I think, to maybe grasp that, I feel like we need to get into a little bit the details of like the implementation, like how this is being implemented so far. So I've just talked about Landsat and Sentinel. I think you guys are using mostly Sentinel at the moment. Like what kinds of input has been used at the moment? What are we talking about?
So we started last year, towards the end of the year. We released a version only with Sentinel, which is one of these open data satellites with visual and radar. Now, the one we just released last week, it's universal. It's amazing because we figured out a way, and I can tell you how, that we can use exactly the same model and we've given it a lower resolution like Landsat, 30 meters visual, high resolution at 10 meters with Sentinel-2 visual, also radar data, Sentinel-1, also NAIP data at 1 meter resolution, which is only for the US, and also there's a data set in New Zealand, which is 5 centimeters, also visual and infrared. So we figured out a way that as long as it's in the spectrum, like visual, infrared, radar,
that's
whatever
what I wanted to get at.
And whatever resolution it is going to understand that and is going to make consistent embeddings. We used, I will tell you more, but basically we use 70 million images of 70 million locations, roughly 50% the Landsat Sentinel, 50% NAIP, and the other one, it's called LIMS, from New Zealand, and from 1 to 10 times per place, so that we also understand a little bit of the dynamics in one place.
Okay, so you have this model. We've had all of this data for a really long time. We've been capturing data of the Earth for a very, very long time. Landsat started in 1972. It's been more than 50 years. So we have this enormous amount of imagery. Now we have transformers, which is this much more recent thing. It's just a few years, which really enables to be able to do that. How do you validate that this works? Because I could totally see we were having a conversation with someone 10 years ago, and they could have said, convolutional neural networks, they're really going to work. They're really going to be the thing that really unlocks this. So how do you get that confidence that it can work? We were talking about, global forest watch, biomass, land cover. Those are a few examples. I want to poke at that a little bit more.
No, of course. And you should. And that's kind of, look, what we're doing is an experiment.
Sure.
Because we saw no one else was doing this at scale. So we pitched to our philanthropic funders to do it, because we care about the what, which is this, but also about the how, which we haven't talked about, which is we chose to be a nonprofit for a reason.
I want to get to that in a little bit. Yeah.
Yes. So this is an experiment. And if it turns out it doesn't work, well, I think it was worth trying. The other bit that I wanted to add before is that not only we give the resolution and the wavelength, but also the location. I think it's very important to realize that the application of AI for Earth is fundamentally different in some ways. One of them is that with text, you have infinite amount of possibilities of text. With pictures of cameras, you have an infinite amount of possibilities. But with Earth is large. There is only one. And I think that is crucially important. Not only is one, there are certain changes that don't happen or happen slowly. Like Washington D.C. is in Washington D.C. always, and tomorrow it's not gonna be I don't know, green blob or a purple thing. So the space of possibilities of the embeddings is much more empty of possibilities than with text. Almost anywhere, I would argue, in the embeddings of text, there could be something because you could make up something of text. But for Earth, it is or is not. And that's where the other aspect of AI for Earth is extremely powerful. As you said, we have archives of Earth from many, many years ago to the present, and we will continue to have, at least for the open data, for sure, commercial will also continue. I think transformers trained like we are doing at a global scale don't need to scale infinitely like GPT-2, GPT-3, GPT-4, all those things, because it's going to get to a point that the variability that this AI is able to understand already covers a large amount of the variability we see on Earth. This is something that I argue, and people, especially in biodiversity spaces, don't agree with me, but I still think it is the case, which is that to a large extent, Earth and Earth changes are limited. Yes, climate change will make things different, but the ways it's going to make it different are the same ways that already exist. So Madrid might become a desert. It will be a desert that looks like Sahara. It's not going to be a completely new kind of thing that is going to be completely new embedded in space. That's why also AI for Earth is not an infinite run to the always better, bigger, faster. It's going to take maybe 2, 3, 4 efforts to get to a point that we can represent any input data with an embedding with a small-ish loss, which answers your question. How do we know these are good? Well, we know we have a mathematical definition of how good the embeddings are able to replicate the input. If the loss were zero, I would tell you that it is lossless. It is not zero. It is some measure. That's why also I always promote that together with embeddings, these vectors, you should also publish your losses. So you get an idea of how well the AI has been able to represent the input in an embedding. If the loss is very low, it's either because the model is really good or because it was very easy to cheat. Like, for example, super cloudy. Super cloudy data is really easy to embed, just white.
Yeah, it's white.
But if the embedding is very high, it means there's something on that image that the AI couldn't really figure out. Maybe worth training more on that, or maybe worth seeing why that is. Why is that change making the AI confused? It already gives you a ton of information. And we can argue what kind of losses we should create, or what kind of applications of benchmark, which is something that does not exist on AI for Earth. But we have ways to answer those questions, which are very important. How do we know? When I say clay is the best model, what does it even mean?
I want to get back to this point that you mentioned where biomass experts disagree with you. I remember you've mentioned this to me before, this idea that like Earth has a limited range of possibilities. And which is why now in time, like, is a good time to start working on this problem, because we're reaching the point where we can solve a lot of problems, and Earth, we have a lot of data for it, and it's a restrained problem. I think this idea has been living in my head ever since you told me about it, and I've been trying to think about what that means. And what the way I understand it is, if you start from image or text, there's a certain, in images, you can have a pixel can have, it has three colors, and it has just a range between 0 and 255. And so any image is basically, you would take any random number, and that's an image. And you can narrow that space down to like an image that actually represents something. If you were to just randomly generate pixel values, most of them, like over like the over majority of them would be noise, would be nonsense. And so then you can narrow it down to something where you can show an image at someone and they say, yes, this is a thing. So we've already narrowed that space down. But Earth is actually even smaller than that because there's only even a subset of representations. Like we know in climate, for example, in weather modeling, the temperatures are also between a range. It's not going to be 10,000 degrees on Earth. It might be one day down the line, but it's a fair assumption to say that, historically, even with a margin, temperatures are within a range. Wind speeds are within a range. Tree height is within a range. You are not going to have a tree that is a kilometer high. And so with all of that, what I understand is that even taking these very, very large assumption, let's say a tree can only be a kilometer high, it's already absurd, but it's a safe enough. Like we can narrow that problem down to the point where it is learnable in a way. And it's very scary to think that like the earth is incredibly rich and incredibly diverse. And so I think there's something inherently, philosophic. Like we don't want to think that like it can be put down to like a small learnable thing. But I think if we take it from the information space of like, an infinite canvas of pixels, we can really narrow it down. I think that's what you're referring to, is like there's a certain set of ranges of all the variables that are possible on Earth, at least to a certain, very likely probability.
I don't think it removes any beauty. If anything, it makes it more beautiful because then you can think of Earth semantically. It's a fractal. But the more you zoom in, the more details there are. Like every tree is different, but any human would recognize a forest. The types of forest are understood, and AI in general can do slightly better than an expert on a field. That's kind of rule of thumb for deep learning, is AI can do slightly better than a professional on that field. And yes, if you zoom out a lot, a forest is a forest. If you start to zoom in types of forests on depending on the location, depending on the species, yes, and then you zoom in all the way to trees, there's a lot of variability. I am not saying that a model will be able to go all the way down to trees and say that they are all the same. I'm saying there is a sweet spot that answers most of the applications where the space of possibilities compare to what actually happens is much smaller. I'm not saying that it's small. I'm saying that it's much smaller than that has worked on text or images. In a way, what you describe, when we're talking about, is what the technique called stable diffusion or diffusion techniques in AI, which is basically you add noise to a thing and then you remove noise. When you add more noise and then you remove noise. When you start from very noisy or random images to the actual image, what you are doing in that process is forcing the model to pick with the prompt of a person. So you say, I want to see a person, and then it starts in this stable diffusion thing with random, and then goes to the cluster that it knows people are. And it knows it's in that place because it has made that index. And then it's going to be forced, once it's close enough, it's going to be forced to pick one of those. And that's why every time you see something different, right? So if you ever seen how a stable diffusion starts to generate, makes a blob, there's more resolution, there's more resolution, there's more resolution. What I'm saying is that the same thing happens with Earth. But in that case, there is not like always the same person or always the same person looking in different ways. The amount of possibilities that you actually see on Earth is a very small subset of the amount of mathematical possibilities of multiplying, as you were saying, 8 bits plus 3 channels or whatever thing it is. And because we know the technique works for text, because we know the technique works for images, it should work much better for Earth.
Mm-hmm. And I think this is where I really appreciate you mentioning like publishing that loss is also really important. I think it goes part of knowing where the limitations are. Like, what are we leaving out? Like, what are, I think it's like in, if you do, uh, physics or science, like you, you started in astrophysics. You have to make assumptions. You have to make an assumption that like we are simplifying the model of whatever we're trying to represent. Like you have to make assumptions and simplifications, and those assumptions and simplifications are really important to keep in mind. I feel like that loss is basically a representation of what are we leaving out and assuming. So to your example about trees, like we are going to assume trees are a simplified version of what they really are. But
Mhm.
if we went
Yeah.
to the microscopic, we would see differences.
I would even argue that when we said the 90% correction, the 90% capacity to replicate, I would argue that a lot of the rest, the remaining 10%, come from places where the losses are bigger.
I would imagine like outlier events, basically.
Mm-hmm.
So
Yep.
something that wasn't just deforested, but like a city was built, or like a flood happened, like these outlier events that you might not see as often.
And we know something that is very well known is that the transformers and the mascot encoder and the techniques, most of the techniques we used, they smooth. They smooth out the extremes.
Yeah. Very
So
built. Yeah, of course. Well, you're trying to get, every time you're trying to represent something, by, be it an equation or a model or anything, you're trying to find the overall general trends. You're basically creating stereotypes. And there's a reason why, also the brain works with it's very handy. It doesn't mean that it's correct all the time, but it's incredibly handy to be able to have a rule of thumb that, like, hey, in most cases, this is right. But it's being aware that in some cases, it's going to be wrong. If Madrid became a desert tomorrow, that would still be a bit of an outlier event. We know what range it would be in, but it would still be an outlier event.
we want, if Madrid became a desert tomorrow, we would want the loss of that to be high. And
So
we
you
give
can
the
find
location
it.
and the
Mm-hmm.
time to the model. We are not forcing the model to pay attention to the location, but we give it to it. And we haven't tested it yet because that's the we've released the model. We've proven that it works very well. But now the work continues and to test it and see what are the limits and where it works better and worse. And this is one of the tests.
We've laid this out. This sounds like it's incredibly expensive computationally. Like just the amount of data that you need to process. Like you're trying to create this little piece of paper of what the Earth represents, to use that analogy. So there's a lot of work that's needed to do that. A lot of computation that requires a ton of money. And so I want to get into the structure of the foundation that you've started, because it is a foundation. It's a nonprofit that you've started. You've decided to go in that direction. I want to ask why you've made that decision, and then I want to make probably a parallel that you've heard about before, which is OpenAI, which kind of started on the same premise. But I want to spend a little bit of time on how you are able to fund this project and how you're thinking about the money.
We made a foundation to make foundational models.
Yeah, that's
That
pretty
was the
funny.
reason. No, okay, so the what, it's clear. I hope by now everyone else is as excited as we are, or similarly excited as we are for the what. Then we should talk about the how and the when. The when is also interesting because I think this could not have been done 2 years ago because the transformer didn't exist. And I don't think this would be able to be done 2 years from now because the space will be already dominated. And now we have the window of opportunity to have a say on the how. To say, hey, I know this is going to happen. This should happen. I have no idea why OpenAI or others are not using Earth data for the GPT-4o or all of this Claude and all the others. I genuinely would love to know why they are not using Earth data when it's just there and has no legal issues and everything. But anyway, we have a window of opportunity to define the how. And this is when we thought about, okay, what is the governance for an AI for Earth if we choose it? And talking with experience, also having done similar things, my co-founder Dan Hammer and I, we decided that we could do this for profit, make a VC, and there are a number of companies doing this. But if we're able to raise philanthropy money for a nonprofit in the US with these legal tax benefits, then we, number one, as a foundation, we cannot be bought. There's never an exit where a company buys the products we create. Number two, we are mandated by law to create public value. We cannot do this whatever we want to do. And number three, we then, if we only touch open data, and we only touch open data, and we create open source, fully open source, then our products can be obviously used by nonprofits, journalists, academia, all the open space, but then also by companies built upon their models on our foundational model and sell it. We want that. We believe that the basic understanding of Earth, that semantic index of Earth, the basics of it, as understood by open data, should be open, just like the data it comes from. And if you have commercial data or you have commercial interest for because you require very high level of accuracy, there should be a space for commercial. There should be a space to charge for fine-tuning this with the specific labels or fine-tuning this with the specific data. So by doing this as a nonprofit, we ensure that we create a world that is not just amazing models commercially and nothing else, and we instead create a future where the basic understanding of Earth for everyone in a way that anyone can adapt, make their own, and build and do whatever they want is very high. It's as high as the data promised. When Sentinel and Landsat promised to do a lot of value, it was not because of the pixels they create, but because of the semantics and the information contained in the pixel. It just was really hard to understand those semantics. What we are doing by that is freeing the semantics and putting that on the same level as it was intended. So, our project, I would say that it should have been done by the providers of the data. Maybe it will be done. And NASA indeed is making other models similar to the one we create. We can talk about the differences. But that is why we chose to do it as a nonprofit to enable the most impact, both nonprofit and for profit.
How do you go from like it would be nice to do a nonprofit to actually being able to raise? I think so far you've raised 4 million, and plans for more. How do you go and say, hey, we're going to take this? We're going to need a lot of compute. We're going to need a lot of GPUs. We're going to need a lot of storage. And we're going to need a lot of talented people to work on this. And so this is going to require a lot of money. What is the selling point? You talked about, the tax benefits, but I'm sure that's not enough. How do you convince people that they should give you their money and basically give it away to these efforts for nonprofits?
As you say, it's very expensive. We raised 4 million and we've spent a large portion of that. Just the compute of the Model B1, I estimate, is been roughly $500,000 of compute. And it also certain amount of emissions of CO2, which is something we can talk about, which is worth talking about. What we are trying to do is to say, hey, we'd rather create a nonprofit that works in the open, that spends $4 million in creating one amazing foundational model for everyone, than every single company and NGO doing smaller, worse models because they might not have the capacity to spend that much money on doing that. So instead of having 10 companies spending $1 million in a model that is subpar and will not compete with others, why don't we create a nonprofit that makes a better model and gives it to everyone else? That's part of the pitch we give. It's on the capacity to affect change in the world, and especially high net worth individuals who believe in those things. This was the case of Smith's Futures, which is the one of our founders. Another one was Grantham Foundation, who really cared about the application of biomass. So basically, it is application based. They really wanted to improve the way we estimate biomasses. And we tell them, hey, we can do that. We can also do a million other things. And by funding this, you will also help create these other million other things. But yes, we will do exactly what you're trying to do. We will help create biomass better ways. And then also support from AWS, because of course, as a cloud provider, they also have the interest to figure out how to do these models and how others can build upon these models. So they also supported us with compute. It is basically visionaries. It's philanthropies that are visionaries that see the value, or philanthropies that are really concerned in a specific application. And we do kind of like a double play where we provide the horizontal tool to be applied in one vertical, and we go together to say, hey, you want to do biomass better? Then we can do that.
The parallel to OpenAI is pretty obvious here, as to like, we're going to build basically like what ChatGPT was trying to be. Very famously, OpenAI isn't very open anymore, and there's been a lot of conversations around that. And I think one of the, if you were to listen to Sam Altman, like one of the reasons is just like how much money this requires to generate. And I think they, the sort of assessment would be that they didn't realize how much it would cost, and they had to pivot to try to just raise a lot more money. And it's easier to get funding if you're a for-profit.
It's a long conversation, but yes,
Sure.
On one side, OpenAI is a similar idea, both because they're a nonprofit to try to do that, but also because it is very new and we haven't really figured out, and we are looking for help to figure out the governance of this. But I think it should make sense for a nonprofit to figure out there are certain activities that make sense to make a for-profit. And then you create a for-profit site that it's okay if they get sold out, it's okay if they charge money. Of course, nonprofits can do revenue generating activities, but they're not really designed for that. They are designed for public value. And there are cases of like National Geographic or Signal or others that are nonprofits that own for profits. OpenAI is the most famous that went weirdly in a direction.
I think that's the I think the fact that there is a for-profit part, and you have to pay for a faster version of ChatGPT. I don't think that's the problem. I think the problem is that this premise that it would be an open model that anybody could be used, that went under, and so. It is definitely a complicated question, but babe, let me ask you the same thing basically. Do you think it is possible, given the cost to build and maintain models like that, to do it completely in as a nonprofit?
I will propose a litmus test to if something is open or not. And the test is, imagine tomorrow it closes. What value remains? The value that remains is the value that was open. If you are a for-profit company and create an amazing product and the world depends on your amazing product, that's fantastic. But then if you go down or you sell or you go bankrupt or whatever, a lot of the value disappears. But if you build in the open, by definition, you detach the dependency of yourself, or you should detach the dependency of yourself. If Clay disappears tomorrow, the documentation, the model, the weights, the license, the legal clarity remains the same. If we sell the same, if OpenAI sells to a company or disappears tomorrow, GPT-4 would disappear, or GPT-3.2. I don't know what was the last one that was open. The ideas will remain, and others would do that. But to me, it's a litmus test if OpenAI is open or not. And it's clearly doesn't pass that test on the GPT-4.
Yeah. But my question is, like, do you feel, and I mean, I'm sure you have, I know the answer, but do you feel confident that it is possible to build and maintain this, given the amount of resources that it takes completely in the open? Like, is there enough philanthropy out there that can sustain a project?
For AI for Earth, I think it's a special case because, again, it's a limited effort. And I also think that because of the increasing urgency of the application of AI for Earth on climate change, sustainability, biodiversity, it's only going to go up. And the data is there. And people are going to start to say, hey, why does it take so much time to do this? And there will be always commercial companies that provide those efforts. But once we start to set the stage of what is possible in the open, I believe that would be the case. I believe, and we've proven the case, that there is enough interest. Is that enough? We'll see. If we or others doing the same thing we do, doesn't need to be us, but if we or others create open AI models of Earth, the answer is yes. If not, I think the answer is not yet. I don't think it's a no. I think this will happen. We just need to wait for the urgency to arrive to those in position to fund this.
I definitely appreciate that you are trying to do that, and that you have the humility to say, like, we'll see how it happens, and we'll give it a shot, and like whatever happens, as you mentioned,
Because look,
the
companies
projects will.
disappear. Like VC companies, 90% of the companies disappear, and
Yeah, for
nothing, no
sure.
one bats an eye. Yet, most of that value disappears. A lot of nonprofits disappear too, but a lot of the value they create, if it's open, it remains. And that's what makes me happy. That it doesn't matter. Everything we create, everything we put out there will always be creating value, regardless if we continue working or not. Of course, we want to continue working. Of course, we have amazing, concrete ideas. We just got started. But it fulfills me to think that we are doing it this way because it ensures lasting impact.
What do you see? You said in 2 years that opportunity window is going to close. There's going to be a lot more things. What do you think this looks like in a couple of years? Let's say everything goes well, you get enough funding to keep going. Where do you think, we have another conversation in 3 years. Where do you think Clay is, whether it's still you or not? What do you envision that project to look like, or the applications of it?
You can think of it as the Wikipedia of Earth that is not built by humans, but is built by Earth itself as being registered by satellites. It's a semantic index that it's a computable semantic index that anyone can ask questions, can chat with. Things like, I want to know more about the deforestation or degradation, or what are the biggest changes. All those are semantic questions. And if that becomes a standard demand of people, of society, of nonprofits, of governments, of NGOs, but also becomes the baseline for commercial companies, it should be a public utility. It should not be a differentiator of a startup business. I believe that basic understanding of Earth, because we have open data, basic understanding of Earth is at reach to be also a public value.
There's one thing that's looming in the back of my head as I hear you say that. If we're able to query everything everywhere kind of all the time, there's also, a bit of a dystopian privacy aspect to it, of if you're able to see everything all the time, like there's this just uneasy aspect of, like, sometimes we don't want everything to be searchable. Not for the climate aspect. Like for this, I think we definitely want to be able to say, like, we want more transparency on where deforestation is happening. But there's also the individual aspect of, by individual, I mean individual person. And that is it's a very broad topic, and I'm not even quite sure where to go from it. But is that something that you're thinking about? Is that something that's also in the back of your mind?
Very much. The how to safely deploy AI is the reason OpenAI decided not to be open anymore. And they have their arguments to do that. I think we are very far from having to make that choice or not. Number one, because so far we're only using open data. Is we are not making any other, we are not using data at high resolution enough that is not open. So this is already available. And the questions of ethics, we basically can piggyback to the questions of ethics of Landsat or Sentinel
Right,
or
I
NAPE,
see.
because we make Of course, we make indexing easier, so we have a bigger responsibility.
Yeah,
And that's
absolutely.
also why I mentioned before the governance of this should be clear. When we publish our models, we use the Stanford Transparency Index, which addresses some of these issues, but also it's a very low bar, but we release our model completely open with a license that prevents uses that harm people. And it's a blanket statement. Of course, it depends on people abide it or not, but that's the best we can figure out so far. And we are very open that we need to answer those questions because clay could be used with commercial data for applications that are far from what we've intended. It's also a long conversation, but the core of it is to say what better way to solve this question than doing it collectively in the open. We don't need security by obscurity, like thinking that this is not happening. This is happening. This is happening in the open. Let's work together to figure out how to do it.
We've touched on commercial data a couple of times. Where does that fit in at the moment? Are you using any? Are you planning on using, or are you leaving that up to the companies that are doing all the analytics or the image provider and saying, hey, we just create the foundation model. You can pre-train it for whatever
Yeah.
you want on your own data.
Yep, exactly. It might seem the way we are so heavily open, radically open, it might seem we are against commercial uses. We are actually the opposite. And I've tried to explain that we are basically giving any commercial startup or company a literally multi-million dollar model on day one. And that's by design because we want them to create amazing products starting from a much higher place. We do not touch commercial data. We only touch fully open data because if we start to inherit the licenses of CC BY, like for example, if we need to do attribution, like Satellogic, for example, released a very large amount of really high resolution data recently. We cannot use it because it's CC BY. So then we wouldn't be able to say, probably because the clarity or the legality of that is unclear, that play by Satellogic or partially by Satellogic, which also means that then competitors of Satellogic might have more problems building on top of that. By remaining open, we create a really good space for commercial players with which we work and with which we want to work for them to build on top of that.
Yeah, that's another big advantage of what you're doing compared to what OpenAI is doing is, I mean, I don't know if it's settled at the time that we're talking about, but there's, the New York Times has filed a lawsuit against OpenAI for basically using their, copyrighted material. There's a huge debate in a lot of the image generation. A lot of artists are really pissed at everything that's going on.
Yep.
And so,
For a
in a
reason.
way,
Yeah.
that is a clear advantage to be able to say, hey, everything here is already open.
But that's why, just for legal reasons, that's why I'm surprised no major AI player is touching geospatial data. It is the most cloud-friendly, structurally ready, legally clear, comprehensive, global,
Yeah.
historical data set modality of any. And it's not being used. So great, there's space for us.
The other big data set that I can think of, we were talking about Wikipedia, is OpenStreetMap. Are you using? We've talked about images a lot. Is there any other types of inputs
Yep.
that you're using? I'm thinking of
So
OpenStreetMap, but is there anything else?
not on the model itself, but we use in OpenStreetMap because remember those embeddings are mathematical numbers which humans cannot read easily. So we use OpenStreetMap to generate human labels of those embeddings. It's kind of simple. So basically, we take for every image that we make an embedding, we take the OpenStreetMap description. There's a house, there's a road, there's blah, 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 blah. And then we create an encoder, which is, remember the encoders? We create an encoder that makes an embedding that should be as close as possible as the embedding of the image. So once it's trained, the embedding of the pixels and the embedding of the description from OpenStreetMap should fall in the same place. So when I type, I want to search for houses, it creates an embedding that will be close to the embeddings of images that have houses. We call it text to earth, but we are not using, but to your wider question, there's a lot of things we don't use. We don't use labels. We don't use ocean data. We don't use atmospheric data. We don't use climate or weather. It's basically the surface.
Do you see those as being like the next steps?
There are other people are doing that. This kind of started in a way with Pangu weather, which is the same thing, kind of the same thing for the atmosphere to predict climate. That was able to predict way better, way faster, way cheaper than the physical models. And there is a group in Italy, CMCC, which is doing the equivalent for the volume of the oceans. Okay. We do land and coastal. So we can do coastal because satellites, Sentinel and others do some coast, and there's a lot of applications in coasts. But for the volume of the oceans, needs to be a specific model.
You know, when ChatGPT came out, it was basically trained, I think, up until September 21, something like that. And so basically, you had this model that had this context, but it was unaware of the latest updates. And most of the things that you want to know is like, hey, what is going on right now, or like, what is the like, help me understand this thing that's going on, or you know, there's been an update to something and you want it to be aware of that. And so one of the things they've done, I think, well, there's two things. There's you basically retrain it on a data set that's more recent, or you just give it the awareness of like, hey, you can go do a query on the internet. Here's how you do it on Google, and go figure out the answer yourself. What is, if you've thought about it, like, what is your approach? Are we going to have a foundational model, a V2, that it's just and like a recurring release where like, hey, this has been trained on 2024 as well? Like, what is the update cycle that you're thinking of, if any?
Yeah. One parallel, the biggest parallel we aspire for with ChatGPT is, I'll say that first and then I'll answer the question, is sure. Another one, which is that I don't think ChatGPT won because it was technically better. I think
sure,
ChatGPT
won
the UI. Because it's the simplest to use. That is key. Geospatial analytics, it is estimated to be $100 billion, which is like this market of Starbucks. Of course, there are many ways to do that. It's tiny. It's really tiny compared to the space of sustainability or climate change and others. But in terms of users, Esri, which is the dominant player of analytics, says they have less than 1 million users. Double that, 2 million users. Are we building AI for it for 2 million users or for more? ChatGPT has like 1 billion users per week or something. Usability. So basically, all we're doing is how can we make embeddings usable? That's also why we made an app to make it easier. That is the guiding light of what a lot of the things we do. But to your question of keeping it updated, the reason ChatGPT needs to be updated is because the way it works is that you ask a question and it is designed to continue the phrase. That's what it does. It continues the model itself is trained to continue the sentence. In the equivalent of AI for Earth would be to say, give it an image and fill in the gaps. Remember that we remove the gaps and we put the gaps in. If that is what we were doing, yes, we would probably maybe need to keep it training the model so it could fill the gaps with new data it has not seen. I don't think that's the case because new text, new news, new developments in the world for ChatGPT are fundamentally new spaces in the embedding. We talked about this before. On Earth, it's not going to be fundamentally different in most cases. So in that sense, we don't have that problem. The equivalent conversation, which ChatGPT does not use, but others like Perplexity and others start to use more and more, is that you create embeddings. Just like we create embeddings of the Earth, and we will create embeddings for every single file, because it's a limited number of files. It's a large number of files, but there's a certain number of files at Sentinel. We can create embeddings for all of them, and we have the complete set. You would need to create embeddings for the entirety of internet and keep making them, and then search on that database to have the equivalent of what you're talking about. That's not what ChatGPT does. It continues the text and it uses tricks to do that. So the reason Grok, for example, in Twitter or X is able to get new things is not because it's being trained. It's because it's creating embeddings of the things that are happening and then using these embedding searches to know what is happening almost in real time.
My understanding is then the world is still going to keep changing. Like things are going to move around the world. And so you are still going to have I think about this in terms of like calibrating, basically, at least. Maybe it's not retraining, but saying like, hey, these places in the world have gotten a little bit warmer. So the trees look a little bit more like this, or like these
Yeah,
buildings were removed, or like these trees changed.
yeah.
Do you see that as like needing this recalibration? Like what does that look like?
I think once we have a model that is able to create low losses consistently for the archive unearth, which I think is going to happen. I think once we get good losses with a global coverage, I would be surprised if the losses increase a lot in the archive. I genuinely believe that a good model will be good in the archive and in the future. Maybe not, but again, let's keep track of the losses. For as long as that happens, I think maybe Clay version 2. Like we want, as mentioned, we want to create embeddings for the archive. We will not do it until we have certain confidence that the embeddings are of quality. It would make no sense to spend the compute to create embeddings for the entire like 50 petabytes of data
Yeah.
if we don't know that is. But one that exists, once that the model is trained, creating embeddings is extremely fast. So my hope is to convince AWS, Planetary Computer, and others that every time a new image comes, you make the embedding. It's almost for free then, and then you keep having
I
a
see.
semantic
I see.
index
So you're indexing it as it goes
in
with
real
the
time.
with the previous model. I see. So that's basically like the inference that you would have if you trained a model
Exactly.
on a
Exactly.
segmentation. I see.
Yep. Yep. Do embeddings and losses because you need to do the embeddings and then the loss to see how good it
Yeah.
is constantly.
I saw in one of your announcements that I think I understood that like you are not working on the next model right now, but you're working on the applications and like making sure that it gets used. So a little bit in a way like what OpenAI I think has been doing is like they're not all their efforts are not always on like we're training, GPT-5 or 6 like, but it's rather on the usability aspect as well. And I
Yeah, we
understood
are
like
we are orders of magnitude of the problems they have because I
for
understand
sure,
that
yeah,
they
but
are.
my understanding is like
Yeah.
you're not working right now on like training the next model at the moment. Um,
No, we just did a big run of training. It was insane. Like during the training, these 32 GPUs were churning 10,000 images per second for like a week nonstop. Like imagine the amount of human labor that we are replicating here to create those little pieces of text. It's insane. So we have something we believe has a lot of value, but we don't know. So that's why we switch from exploring new grounds to exploiting what we have so we know where it works and where it doesn't. So once we start working on the next version, we are more informed because now we are starting to understand what the intuition of what the model is doing.
I didn't ask actually, but like, what is the do you said 70 million images? Um, I just want to ask like to get a sense of scale, like how big are the embeddings compared to the data set in terms of like storage? Do
Well,
you have
if
an
you
idea?
if you take Sentinel-2 with all the bands, because we take all the bands, I don't know, maybe 200 megas per image, and the embedding is 700 numbers, which is like 20 cas. So
Okay,
it's 20
right.
kilobytes. So it's like an absurd amount of compression.
Okay.
But if
What
you but if you have as very small image on, I don't know, one channel, the embedding can be bigger than the input because the embedding is always 768.
yeah, I
Doesn't
see,
matter
I
if
see,
it's
I see.
embedding Las Vegas, that is embedding flat ocean. It's always going to be
That's
68,
quite
if I
interesting as
remember
well.
correctly.
Yeah. So what is um, you know, model version 2? What do you think would be needed to do that? Is it like you're taking advantage of whatever comes after transformers, and we can get us even smaller loss? What do you think comes
I
after?
think part is going to be architecture, because as you say, the things developed. Like one of the, we use a series of tricks that have been developed to accept any kind of image. Da, da, da. So I'm sure there's going to be more development how to do that. But also the training mechanism, mask autoencoder or Dino or others. So one is architecture, others learning path, but also what data do you use? Like for example, we don't know if it's better to have double the data and the same number of runs, epochs, or same amount of data and two runs on there. This not for text. There's this Chinchilla paper and others have figured out the answer to that. And we have some intuition of this conversation already on why we believe it's better to have more data in less time. But maybe version 2 is a model that is not like 20 epochs, 20 cycles of all the data, but it's only one cycle of the data, but 20 times more data. Because the Earth data is so cloud friendly that you can dynamically query it instead of having to prepare everything into a little chips of things like text needs to do, or like we had to do for this version, but we hope not to do. So version 2.0 might be that, might be a completely new architecture. I don't know. I suspect it's going to be mostly about how we train the data and little tweaks to the architecture, but who knows?
I want to take a completely different direction here. The first time I had you on, we talked a lot about impact science, and we talked about your journey from academia to working on World Bank governmental agency, and then you were at Microsoft working on the planetary computer, and now you're at a nonprofit. So it seems like you've seen like all the flavors of how one can work, and all the governance basically that one can have. And I'm curious to ask, like, do you think about that as well, about like having tried all of these and then like landing at the nonprofit? Is there some changes that you're really seeing in the way of working, or is it just this just high level, how the governance is, how the license ends up being? Or are you seeing changes in the ways people are working? This is moving a little bit away, but I'm just really curious to ask about the ways of working as well.
It's a good question. As Stephen Brumby said in one of your interviews, I had all the email endings possible: .org, .com, .mil, .everything when I was doing my postdoc.
Yes.
So large companies, largest company, Microsoft, and the smallest, an NGO. Yeah. So I think I've become less dogmatic, more pragmatic. I don't think any option is fundamentally wrong, but all options come with opportunities and costs. Like, for example, one of the things I think we over index is that large corporations cannot innovate, or startups need to do VC, or nonprofits are basically humanitarian aesthetics, like they need to sacrifice themselves. And there are ways to do everything your own way. Like, for example, we're a nonprofit, but we raise $4 million, which is a lot of money for most nonprofit. I'll be spending a lot of money. I don't think it's being a nonprofit is about being as frugal as possible. It's about delivering impact to the public. And if it means spending a lot of money, well, you better have a good idea how to do that, how to raise that money, or how to create the lasting impact. Not all large companies are driven by profits and growth by 20% margins like Wall Street demands. Um, I found some of the most passionate and motivated people when I was working at Microsoft. Even though when I was growing up as a kid, Microsoft was kind of the evil corporation. So when it comes to impact science, I think it's really in anything you do to just understand what are the challenges and opportunities and work with them. As a nonprofit, we have the challenge of the funding and we might not get it. That's fine. Let's build it so that even if that happens, we maximize the impact. It's a large corporation, you have different, it's understanding the limitations and then driven by the impact you want to do. I have been in many places, in many kind of institutions, in many kinds of governments, but I've always done the same thing, which is how do you leverage science and technology for impact in society? And there are ways, and there should be ways for each of those players to play a fundamental role on doing that.
I still do want to round up with the same question every time, though. I didn't ask you how you describe yourself, but I'd like to ask if you have a book or a podcast that you've listened to recently that you think would be worth sharing, that we talked
Oh,
about.
this.
Anything recently that you've, I know you've become, you had just become a father when we first chatted, so I know you've been very busy. You've started a nonprofit, but do you still have time to read and listen to anything interesting?
Oh, I find the time. It really helps me to and fiction books and also nonfiction. On related a little bit on this conversation, one book I really want to recommend is called The Thousand Brains Theory, which is, to my knowledge, the only book that fully connects between neuroscience and neurons, like in our brain, and intelligence. We talk about intelligence and we talk about neuroscience. We always say that where intelligence is in the brain is unknown. It might well be unknown, but that book is the only book that provides a falsifiable hypothesis of how that works. And I was going to summarize it, but just go read it because it is so thought provoking that I had to actually stop reading the book at some times to just think about what I had just read. It's a fascinating book. Then, as I said, I'm a dad. Um, I had two kids since one kid more since we last spoke. I have a 3 months old and a 3 years old. And one book that I've loved a lot, that's a little bit contrarian, but I really like, is called Bad Therapy, which talks about how our generation has been raised in ways that might make our kids more dependent on us or less agency. And it was jarring, but also important to read the book because some of the most normal advice I've seen and I've been educated with, now I realize that there are ways to do that. So that's two books that I could recommend.
Have you been listening to any podcasts?
I like Pivot. I like the podcast Pivot with Kara Swisher and what's the name of the other one? Anyway, yeah. Um, I listen to that one. Not really much more. I just don't have time. Music, I would say.
Yeah.
Recommendation of podcast, music. I don't have any specific thing to recommend, but we sometimes get hung up in audiobooks and podcasts.
Mm-hmm.
And then I go listen to my favorite playlist and I'm like, wow, this is so good. Listen to music. It's just catnip for the brain.
I think that's a beautiful place to end this conversation. Thank you so much for your time, Bruno. I'm very excited about what you're doing and that you are doing it. And I'm very much looking forward to seeing what happens next. So thanks for coming on and talking to me about everything you've been working on.
Thank you for doing this.
Hey, thank you so much for listening to this conversation. I wanted to take a moment to thank the sponsor of this video, but also all the people who financially support me on Patreon. If everything goes well, these conversations should feel and sound seamless and effortless, but there's a lot of work that goes behind the scenes. I try to research and prepare these as much as I can to know who these people are and what makes them interesting and what would lead to a good conversation. I'm incredibly thankful to all the people who support my work on Patreon, meaning I can do a little bit more of it. This podcast started out as a way to learn more about the people in this industry, but I've also started making educational content on another YouTube channel that I'll put a link to in the show notes. And I want to make more content explaining how satellite images and maps work to a broader audience, as well as continuing to research the guests for these podcast episodes. So if you value the work that I do, I'd like to ask you to please consider supporting my work on Patreon. There's also some behind the scenes of how this podcast is done and some of the work that I'm doing for these educational videos if you want to learn more about how I do all of this. Either way, thank you so much for all of your attention and your time. I really appreciate it, and I hope you get value from these conversations. Thanks.